Hi everyone, my name is George Butowski and I'll be your instructor for this training session. My home base is located at the Grid IQ Learning Center in Markham, Ontario, Canada. I've been with GE for 12 years and actually started my career with GE as a test technician evaluating the documentation and functionality of the 369 motor protection relay. I then worked with the Technical Support Group Help Desk providing support for the motors and meters group. My next role was again in technical support, providing support for the Smart Relay SR family relays and applications related to feeders, transformers, generators, and motors. In 2008, I accepted my current role in technical training where I am responsible for the development of the training content working alongside our instructional design team. I deliver training courses either at our learning centers, at our customer site, or by facilitating virtual classroom sessions like this technical webinar. I also conduct training on GE Multilink devices and the full range of multilink protection, communication, and metering products, including specialized applications such as IEC 61850 and the Multilink managed switch configurations. The Grid IQ Learning Center is a state-of-the-art rich media delivery center, which makes it a real pleasure to be working in such a high-tech environment. Before we get started, I want to give you an insight into how we prepare each webinar's content and what you can expect throughout this session. Once we decide on a topic, we build a storybook of content working with various subject matter experts such as technical support, engineering, and product management teams to determine what the precise content should be based upon the latest customer interactions. For example, what are the most frequently asked questions, and are we addressing them properly? From there, we determine how best to create that content and whether or not we should pre-record certain elements to provide improved quality of content and delivery in order to provide the best learning experience possible for the students. That said, this technical webinar will involve both live and pre-recorded elements. At the end of each training segment, we will do a live Q&A session where we will open the lines to address any questions you may have. As the facilitator, I will be present throughout this webinar and will be communicating with you throughout the chat line. Let's address two key questions that are frequently asked during our technical webinars. The first is, why is this session a WebEx session using the internet, but audio is through a telephone connection? The reason we do this is simply bandwidth. Our sessions are for a global audience, and not everyone has high-speed broadband communications needed. Therefore, from a delivery standpoint, we're able to provide a smoother delivery using mixed media. The second question is always, will this session be recorded and made available online? The answer is yes, it will be. More information on this will be provided at the end of this webinar. So, without further ado, let's get started. Welcome to the GE Digital Energy Motor Theory webinar. The webinar will consist of pre-recorded and live presentation. At the end of each part, there will be a summary and a Q&A session. The main objective is to understand the fundamental concepts of the thermal modeling, which include the following: common motor terms, the procedure of correct protection current transformer selection, the motor thermal limits curves, motor thermal modeling principles, and the 5 key elements that comprise the motor thermal model. Our agenda will consist of the following parts: introduction, thermal modeling, and motor protection elements. Part 1 introduces us to the thermal modeling concepts, motor ratings, and CT selection. Part 2 reviews the thermal modeling principles and key elements of motor thermal modeling. Part 3 will provide a clear understanding of the fundamental concept of motor protection elements. So, let's begin.
Motor thermal modeling. The primary motor protective element within a motor protective relay is the thermal overload element, and within GE Multilink relays, this is accomplished through motor thermal modeling. The thermal model uses motor parameters supplied by the manufacturer in addition to real-time data such as motor current as inputs to a thermal modeling algorithm. The algorithm then calculates whether the motor is or is not in danger of being overheated. To provide a good foundation for thermal modeling, we will first start with a review of the following: common motor terms, motor thermal limits curves, the procedure for correct protection current transformer selection. We will then proceed with an explanation of motor thermal modeling and the contribution of each of the 5 key elements that comprise the motor thermal model. One of the most common motor terms is motor efficiency. Motor efficiency is an indication of how much of the electrical energy supplied to the motor is converted into output shaft mechanical energy and is expressed as a percentage. The rest of the energy is lost primarily in the form of heat, which can be damaging to the motor's insulation. There are 5 categories of motor losses. Core losses. Core losses are comprised of 2 components: the energy required to magnetize the core and eddy current losses in the stator core. Stator losses. Stator losses due to the I²R heating of the stator due to current flow in the stator windings. Rotor losses. Rotor losses due to the I²R heating of rotor bars as induced current flows. Friction and windage losses. Friction and windage losses due to bearing and air friction. Stray load losses. Stray load losses due primarily to leakage reactance fluxes induced by the load current. Core, stator, and rotor losses typically make up greater than 80% of the total motor losses. NEMA motor insulation classes. NEMA, the National Electrical Manufacturers Association, has established 4 motor insulation classes: A, B, F, and H. The specification has standardized on an ambient temperature of 40 degrees Celsius or 104 degrees Fahrenheit for all classes. Each class of insulation has a different maximum motor winding temperature rise, in addition to a hot spot temperature, which is an additional temperature rise for the windings that are surrounded by other windings. The maximum temperature rise and hot spot for each class of insulation is as follows. For Class A insulation, the maximum rise is 60 degrees Celsius with a hot spot of 5 degrees Celsius. For Class B insulation, the maximum rise is 80 degrees Celsius with a hot spot of 10 degrees Celsius. For Class F insulation, the maximum rise is 105 degrees Celsius with a hot spot of 10 degrees Celsius. And for Class H insulation, the maximum rise is 125 degrees Celsius with a hot spot of 15 degrees Celsius. In the past, Class F insulation was typically called for in most industrial applications, but with the ever-increasing use of variable speed AC drives and the associated heating due to harmonics, Class H insulation is now more commonly specified. Electrical motor power ratings. The function of a motor is to perform work, and so one of a motor's ratings should be its ability or potential to perform work. Work is equal to multiplying the applied force by the distance it has been applied. Power is a measure of the rate at which work is being done and is equal to the amount of work done over a given time. James Watt wanted to rate steam engines that he was producing in a unit of power that his customers could relate to. Since the traditional source of power had been the horse, he felt that by quantifying the work that a horse could perform into a new unit of power, the horsepower, and then rating his steam engines in accordance with this new unit of power, his customers could appreciate the capabilities of his steam engines. He determined in practical tests that the average horse could haul coal at a rate of 22,000 foot-pounds per minute. He then arbitrarily raised this figure by a factor of 1/2 to 33,000 foot-pounds in 1 minute, or 550 foot-pounds per second, and established this as 1 horsepower. Horsepower has remained as a standard unit of power rating for electrical motors in North America, while in Europe the kilowatt has become the standard. 1 horsepower is equal to 746 watts, or 0.746 kilowatts. To convert a motor's kilowatt rating to horsepower, one can simply multiply the kilowatt rating by 1.341. Service factor. For a given insulation, a motor with a 1.15 service factor has a lower temperature rise than a motor with a service factor of 1.0. This allows the motor to operate close to the service factor without exceeding rated temperature limits of the insulation. When the voltage and frequency are maintained at the values specified on the nameplate, the motor may be overloaded up to the horsepower obtained by multiplying the nameplate horsepower by the service factor. At a service factor load greater than 1.0, the motor's efficiency, power factor, and speed will differ from the nameplate, but the locked rotor current and breakdown torque will remain the same. Current transformer selection. Proper motor protection starts with the correct selection of current transformers for the relay. The current transformers should be chosen such that the full load current of the motor falls within 50 to 100% of the current transformer's primary rating. The current transformer selected must then be checked to ensure that it can drive the attached burden, its own secondary winding resistance, in addition to all series-connected devices at the maximum fault current levels without saturating. The rule of thumb regarding current transformer saturation is that it will occur when the voltage at the current transformer's secondary terminals reach the knee point of the current transformer excitation curve. The knee point can be defined as the point on the current transformer excitation curve at which a 10% increase in voltage produces a 50% increase in magnetizing current. The voltage at the current transformer, or CT terminals, can be calculated by multiplying the total resistance of the CT's secondary circuit, called the burden, by the maximum expected secondary fault current. The burden is equal to the CT secondary resistance plus the wire resistance plus the relay burden resistance. Once this has been calculated, the CT secondary voltage at the time of fault is equal to the burden resistance times the maximum fault current divided by the CT ratio. CT fault voltage equals fault current times burden divided by CT ratio. For example, let's assume that we have a motor with a maximum full load current rating of 285 amps. The first step is to choose the phase CTs. Common phase CTs for which the motor current falls between 50 to 100% of the CT's primary rating are the 300 to 5, 400 to 5, and 500 to 5 amp CTs. The 300 to 5 amp CTs will have the best resolution, and so they will be chosen. The next step is to calculate the maximum fault voltage that will appear on the secondary of the CT as follows. The information required for the secondary fault voltage calculation will be filled into the following chart. The maximum fault current is 6,000 amps. The relay burden is 0.008 ohms. The CT ratio is 300 to 5. The CT secondary resistance is 0.088 ohms. The CT lead length is equal to 50 meters, and the resistance of the wire is 4.73 ohms per kilometer. The total burden is calculated as follows. The total burden equals the CT secondary resistance, 0.088, plus 2 times the lead length of 50 meters, times the lead resistance of 4.73 ohms per kilometer, divided by 1,000, plus the relay burden of 0.008 ohms, which equals a total of 0.569 ohms. Therefore, the CT secondary voltage at the time of fault is equal to the total burden resistance of 0.569 ohms times the fault current of 6,000 amps divided by the CT ratio of 300 to 5, which equals a fault voltage of 56.9 volts. With the maximum secondary CT fault voltage calculated, the third step is to refer to the CT excitation curve. Using the excitation curves for the 300 to 5 CT, we see that the knee voltage is at 60 volts, well above the maximum fault voltage of 56.9 volts. Therefore, this CT is acceptable for the application. Motor thermal limits curves. The motor thermal limits curves consist of 3 distinct segments which are based on the 3 running conditions of the motor: the locked rotor or stall condition, motor acceleration, and motor running overload. Ideally, curves have been provided for both a hot and cold motor. A hot motor is defined as one that has been running for a period of time at full load, such that the stator and rotor temperatures have settled at their rated temperatures. Conversely, a cold motor is defined as a motor that has been stopped for a period of time, such that the rotor and stator temperatures have settled at ambient temperature. For most motors, the motor thermal limits are formed into one smooth, homogeneous curve. The relay's overload element is the main protection element and is the most critical to motor protection. It is always active and cannot be shut off.
Let's summarize some of the key points of this last part. What happens if we exceed motor insulation temperature ratings? Some of the things: operating a motor above the limits of the insulation class reduces the motor's life expectancy. A 10 degrees Celsius increase in operating temperature can decrease the life expectancy of a motor by as much as 50%. Excess heat also can increase the amount of brush wear. The NEMA standard allows a motor with a nameplate service factor of 1.00 to be run up to 150% of its rated current. For a motor with a nameplate service factor of 1.15, it can be run up to 125% of its rated current. For example, a motor with an FLA equal to 100 amps and service factor 1.0 can draw up to as much as 115 amps before the motor is considered in an overload condition. If the service factor is 1.15, then the motor can draw as much as 125 amps before the motor is considered in an overload condition. CT polarity is very important. The polarity markings indicate the relative instantaneous direction of current in the windings. As displayed in the diagram shown here, when current flows through the primary of the CT in the direction of the polarity markings, current will flow out of the secondary of the CT away from the polarity markings. This will result in no phase shift occurring between the current entering the CT and the current being read by the relay. Let's review the burden. Burden is a term used in protective relaying which refers to the total load resistance connected to the secondary. The burden or total CT secondary circuit resistance must be very low in order to ensure that the CT produces an accurately scaled replica of the primary current and be able to protect the circuit properly. The secondary of the CT must always have a burden load connected to it. An open-circuited secondary on the CT acts as a step-up voltage transformer that can result in dangerously high secondary voltage. Therefore, energized but unused CTs must be kept short-circuited to eliminate any chance of injury. A 10C400 current transformer indicates the maximum secondary terminal voltage that the CT can supply is 400 volts. In protective relaying, when the ratio error of the CT is 10%, it is common for the first number to be omitted. For example, the 10C400 is commonly specified as C400. Therefore, any secondary terminal voltage lower than 400 volts will result in the CT operating with an error limited to 10% at any current between 1 to 20 times the rated current. It is very important that the CT secondary current is an accurate scaled replica of the primary current. If the CT goes into either AC or DC saturation, this will no longer be true and the relay may have difficulty properly protecting the power system. A review of the magnetization curve shows a linear increase in both excitation current and excitation voltage. AC saturation occurs when the CT secondary excitation voltage rises above the knee point of the CT excitation curve. In other words, where the curve becomes 45 degrees with respect to the x-axis, the CT secondary begins to saturate and cannot accurately duplicate the measured values from the primary side. Once the secondary voltage rises above the excitation level, the secondary current waveform starts to deform as shown. The result of this will cause the relay to inaccurately read the magnitude of currents. In examples shown here, if 100 amps were flowing through the primary of the conductor and no saturation occurred on the CT, the relay would accurately read 100 amps. If the CT is partially saturated, the relay would read slightly less current. If the CT is severely saturated, the relay would read much less current than if the CT had not saturated. If a CT were to saturate during an overload condition, it would appear as if the motor went into an undercurrent condition instead of an overload condition. DC saturation occurs when the current waveform has a large DC component, which may occur under specific system conditions such as the energization of a large utility transformer. The danger here is that under certain system conditions, the DC saturation may be so severe that the CT output may drop to almost zero. Proper protection starts with the correct selection of current transformers for the relay. This is the responsibility of the system's designer, and the selection procedure can go beyond the scope of this, of course, depending on the application. However, a simple procedure can be used to check whether or not there is the possibility of CT saturation. Let's assume that a load has a maximum full load current rating of 285 amps. We calculate the maximum fault voltage Assume that a load has a maximum full load current rating of 285 amps. We need to calculate the maximum fault voltage that will appear on the secondary of this CT. We take into account the phase C secondary resistance is 0.088 ohms. The length of each wire from the CT to the relay is 50 meters. The calculated maximum fault current at the load is 6,000 amps. With the maximum secondary CT fault voltage calculated, the final step is to refer to the CT excitation curve. Using the excitation curves for the 300 to 5 CT, the knee point voltage, approximately 60 volts, which is well above the maximum 34.6 volts expected at the CT terminals at the time of the fault. Therefore, this CT is acceptable for this application. Now, I've received a question in the chat. There was a question about in the picture, is the primary current equal to the secondary current when you're assuming a CT ratio of 1 to 1? Then in that case, yes it is. If you're the worst case scenario, this is typically the symmetrical, the worst case fault is typically the asymmetrical. So when you're looking at these fault currents, you're basically trying to understand from your system what's the maximum fault current, what's your voltage, what's your resistance of the line, and doing Ohm's law to determine what the worst case fault condition could be. Okay. Now, typically, when we're doing CT selection, there was a comment in there saying that the CT selection should be 50 to 100% of the FLA. One of the rule of thumbs I like to use is for an ideal condition, the CT selection, the magnitude of the CT should be between 1.25 to 1.75 times the FLA of the motor, with a maximum CT selection of 2 times the FLA. So that's to maintain the accuracy and the resolution. Okay. Any other questions?
George, it's Dennis Dixon with Chess Controls.
Yes, Dennis.
We have an application where we have a 1250 horsepower 4160 volt motor, and the starter manufacturer is using 600 volt class CTs. Is that a standard practice, and what are the problems that can arise?
If you're putting a 600 volt CT onto a 4160 volt line, you're basically going to be over magnetizing that core, and it's going to be overheating.
Okay.
They should be selecting 4160 volt CTs to put on the line.
Okay.
It's absolutely necessary. It's absolutely crucial that you select the right voltage level CTs.
Okay, thanks.
You're welcome. So one of the things I commented earlier was, why do we have these different classifications for CTs? Because the higher you go in the C class, the more expensive the current transformers become. So if we're dealing with these projects that have certain budgets associated with them, we want to make sure that we're staying within budget, but not going over our budget. We still want to be able to maintain protection for our device that we're protecting. Okay. Any other questions?
Yes, that's fantastic. I would have a question. Some people apply a security factor of 2 or 200% to the saturation calculation. What do you think about this security factor?
The saturation level?
Yeah, they say that they calculate the fault voltage, and they say it should be below 50% of the knee voltage.
That is absolutely true. To It's the safety factor that's used by the industry. So if the CT secondary voltage should be 50% of the secondary voltage that's generated by the worst case fault. You're absolutely right. It should not be close like it was here in the presentation where we had an example of 59.7 volts calculated and the C value for the current transformer was 60. That is not typical industry standards. So if you produce 30 volts secondary, then you should be selecting a C60 class current transformer. You're absolutely right.
Thank you.
Okay, you're welcome. Okay. Any other questions?
George, this is Pat Kerrigan. Can you hear me?
Yes, I can.
Okay, I just want to comment on the last two questions. That twice the need is based on all the calculations that you've done are based on AC symmetrical waves, and any kind of fault is likely to have a DC offset, maybe a full DC offset, and that saturates the CT in a different manner.
Correct.
So empirically, people use that two-factor because of DC saturation. It isn't quite accurate, but it's good for calculation, so that's why people do it. The other question I'd like to comment on, the gentleman from Chess Controls asked about 600 volt class CTs. That is quite standard in medium voltage equipment. I mean, typically you're putting a single conductor through the CT, the 600 volt class refers to the secondary windings. You do not have to have 4160 class. It has nothing to do with the saturation. It has to do with the insulation of the ground. So it's quite standard for switchgear manufacturers to use 600 volt class CTs.
600 volt class CTs?
600 volt class CTs and medium voltage.
Okay. All right, my mistake then. Okay, thank you so much for that. Okay, let's move on to the next portion. Sorry?
Mark Minute. So what you guys are saying, it sounds like the CT ratio for the 4160 seems to be something in that range, like a 4,000 to 5 CT ratio, or it needs to be insulated for that. But you're talking about the 600 volts. That was for the secondary voltage that comes off the relay. Like that.
We're confusing voltage with current here. The 4160 is the rating of the bus bar or the cable or whatever. The CT ratio is how many turns you put. You put one single conductor through a donut CT. The CT ratio is the number of turns you put around that donut in order to get 5 amps in the secondary under a normal load condition. But it's the voltage rating is 600 volt class. The 4160 has nothing really to do with the CT ratio.
So does the CT have some type of voltage insulation rating for wherever you're sticking it?
Well, you have to have certain clearances on the conductor going through.
No.
But I guess, George, it's probably something that you want to clarify in a future meeting, or maybe send out a write-up on it.
Okay, I can do that. I'll have everyone's email, and what I'll do is I'll send out a clarification on that. Okay. So the question is, if we have a 4160 bus, what voltage classification current transformer can we apply to the bus? Is that correct?
Correct.
Okay, good. Just want to make sure.
With the industrial solutions, and one comment, the bus, when we're talking about a bus going through the 600 volt class CT, the bus has to be insulated. If you have a non-insulated bus, then the voltage class of the CT need to match the voltage of the bus. But if you have an insulated bus, like an insulated cable, the insulation of the cable was already 5,000 volt cable, so you don't really need 5,000 volt weighted CT.
Yeah, these were 5 kV motor leads insulated.
Okay.
That makes sense.
5 kV insulated. Okay. I'll get a clarification on this for everyone that's online here.
Excellent.
Okay, fantastic. All right, let me remute the lines and then we'll continue on.
The conference has been muted.
In section 2, we will review the key aspects of thermal modeling. We will take a look at the motor thermal limits curve and the information that is provided from the motor manufacturer. We'll review what causes a motor to heat up and how much time we can afford before thermal damage occurs within the motor. What are the overload curves used for? What is the function of the overload pickup level? How long does it take for the motor to cool? Which parameters block us from restarting a motor and why? Let us begin with the section called Thermal Modeling.
Motor thermal limits curves. The motor thermal limits curves consist of 3 distinct segments which are based on the 3 running conditions of the motor: the locked rotor or stall condition, motor acceleration, and motor running overload. Ideally, curves have been provided for both a hot and cold motor. A hot motor is defined as one that has been running for a period of time at full load, such that the stator and rotor temperatures have settled at their rated temperatures. Conversely, a cold motor is defined as a motor that has been stopped for a period of time, such that the rotor and stator temperatures have settled at ambient temperature. For most motors, the motor thermal limits are formed into one smooth, homogeneous curve. The relay's overload element is the main protection element and is the most critical to motor protection. It is always active and cannot be shut off. Motor data sheets should be supplied with every motor. Part of this data should be a thermal limit or thermal damage curve, which indicates the amount of time a specific amount of current can be supplied to the motor without damaging the motor. The cold thermal limit curve indicates the amount of overload current that the motor can withstand before damage will occur when the motor is cold, at the ambient design temperature, which is normally no greater than 40 degrees Celsius. Likewise, the hot thermal limit curve indicates the amount of overload current that the motor can withstand before damage occurs when the motor is hot, meaning it has been running at rated full load current for an amount of time such that the temperature of the motor has risen to its rated temperature above the ambient temperature of 40 degrees Celsius. The acceleration curves are an indication of the amount of current and associated time for the motor to accelerate from a stop condition to a normal running condition. In this particular example, there are 2 acceleration curves. The first is the acceleration curve at rated stator voltage, while the second is the acceleration at 80% of rated stator voltage. A soft starter is commonly used to reduce the amount of inrush voltage and current during starting. As can be seen on the curve shown, since the voltage and current are lower, it takes longer for the motor to start. Therefore, starting the motor on a weak system can result in voltage depression, providing the same effect as a soft start. The maximum locked rotor stall time for both a hot and cold motor can be read directly from these curves. The most precise way to protect a motor is through the use of motor thermal modeling. It consists of 5 key elements: the motor thermal limits curve, overload pickup level, hot-cold safe stall ratio, unbalanced biasing, and biasing of the thermal model based on hot-cold motor information and measured stator temperature. This all sounds very complex, but actually you will find it very easy to understand. First of all, it should be pointed out that if the motor has been designed fairly conservatively, that is to say that the portion of the acceleration curve under the motor thermal limits curve is less than 1/3 to 1/2 in terms of trip time, and the motor has been applied conservatively, that is to say that during acceleration or running, the acceleration and thermal limits curve do not cross, then thermal model settings can be set fairly easily. If, on the other hand, the acceleration curves and the thermal overload curves are very close, accuracy in the settings becomes very important in order to ensure reliable motor protection without nuisance tripping. We will use the following model to aid in a better understanding of motor thermal modeling concepts. The motor's thermal capacity, that is to say the amount of heat energy the motor can hold, will be represented by the glass vessel. The lava-like fluid filling the vessel will represent thermal energy or heat energy that has been absorbed by the motor. The sources of thermal energy that will fill the vessel or heating the motor are ambient temperature, motor losses due to current unbalances and I²T, motor heating due to a start. Motor cooling will be represented by the vapor evaporating from the surface of the liquid when the motor is running or stopped, which represents the motor's ability to dissipate heat. The fan is representative of the additional cooling effect of the motor's cooling system, which is commonly a fan mounted on the motor shaft. With this model in mind, let's proceed with our explanation of motor thermal modeling. The thermal capacity that has been used is expressed as a percentage of the total thermal capacity of the motor, and can be thought of as the amount of the vessel's volume that has been filled with heat energy. If this imaginary vessel is full, 100% of the thermal capacity of the motor has been reached, and any further increase will result in damage to the motor's insulation. The motor insulation does not immediately melt. Rather, the rate of insulation degradation has reached a point where motor life will be significantly reduced if it continues to run under this condition. Ambient temperature and I²T heating due to motor losses, starting current, and current unbalances start to fill the vessel with thermal energy when the motor current is above the motor's full load current. Once the motor current drops to or below the motor's full load current rating, the thermal capacity used starts to drop. This can be imagined as the thermal energy slowly evaporating from the vessel. The rate at which the thermal energy is evaporated and the final level that it will drop to is a function of the motor data and load current, which will be covered later in this section. The vessel is also emptied when the motor is stopped at a rate based on the stopped cooling time. Motor cooling times. The thermal capacity used value is reduced in an exponential manner when the motor current is below the overload pickup set point. This reduction simulates motor cooling. Both the stopped and running motor cooling time constants should be entered. A stopped motor will normally cool significantly slower than a running motor. We will examine the cooling rate of a motor and final thermal capacity used under two different current conditions, one at 100% and the other at 80% motor rated current. Running cool time. In the first situation, the motor had been in an overload condition, but is now drawing only 100% rated current, which is below the pickup level, and has a hot-to-cold ratio of 0.8. Using the above formula, we can see that at the end of 5 cooling time constants, the motor will have stabilized at a temperature for which 20% of its thermal capacity is used. Note that the motor came within 5% of its running thermal capacity used after 3 time constants. Stopped cooling time. Note that for the GE Multilin 369 and 469 relays, the values of the running and stopped cooling times which are to be entered into these relays must be 1/5 of the actual stopped and running cool times. Now let's examine what happens to the thermal capacity when the motor is stopped, having a cooling time of 2.5 hours. The stopped cooling time constant entered into the relay would be 1/5 of 2.5 hours, or 30 minutes. When the motor is stopped, its thermal capacity used value will decay according to the same formula. If the thermal capacity used were at 100% before stopping the motor, the thermal capacity used will take 5 time constants, or 2.5 hours, to decay. The values to be entered for the stopped and running motor cooling time constants can be calculated by dividing the stopped and running cooling times by 5. For example, if the manufacturer states that the running cooling time is 1 hour, then 1/5 of an hour, or 12 minutes, would be entered into the relay as the running cooling time constant. Now that we understand what the thermal model is trying to do, let's see how it accomplishes this task with the following hypothetical situation. For a given motor, the thermal damage and acceleration curves are shown in this diagram. From a quick look at the motor curves, we can see that the acceleration curve barely fits under the stall limits portion of the thermal limits curve. The protection relay tripped 10 seconds into the start. The customer notes from the relay data that during the start, the motor drew 600% rated current for 4 seconds, and then the current dropped to 300% for only 6 seconds before the relay tripped. Given that the thermal damage curve was selected correctly, the customer wants to know why the relay tripped the motor even though the current draw did not exceed the thermal damage curve limits. The answer is quite simple and clearly explains motor thermal modeling. The area under the thermal damage curve represents the thermal capacity of the motor, and the area under the acceleration curve represents the thermal capacity used to start the motor. During the first 4 seconds of the start, the motor draws 600% current. This current level is greater than the motor's full load current rating, and therefore the percentage of thermal capacity used will increase. The vessel will fill. From the graph, we can see that if the motor drew 600% for 5 seconds, 100% of the motor's thermal capacity would have been used. The motor draws 600% for 4 seconds, so 4/5 or 80% of the motor's thermal capacity was used during this portion of the motor's acceleration. This can be imagined as 80% of the vessel being filled with thermal energy. To determine how long the motor can run when the motor's current draw drops to 300%, the thermal capacity already used at 600% must be taken into account. From the graph, we can see that motor can draw 300% of its rated current for 30 seconds if no thermal capacity had been used. Since 80% of the motor's thermal capacity had already been used, which represents 24 of the 30 seconds available at 300%, the motor can only draw 300% current for an additional 6 seconds. This can be represented visually by moving the area of 4 seconds at 600% current into the area of 30 seconds by 300% current. Now the answer to the customer's question is quite clear. We can see that when the motor's current draw dropped to 300%, the relay could allow the motor to continue to run for an additional 6 seconds before the motor's thermal capacity used reached 100%, at which time the relay had to trip the motor. This is why the relay issued a trip command 10 seconds after the motor started, even though the motor's current draw never exceeded the thermal damage curve limits. In effect, the relay is calculating the integral of the load current. Start inhibit. Upon a start, the inrush current is above the motor's full load current, causing the thermal capacity used within the motor to rise rapidly. GE Multilin motor management relays learn the amount of thermal capacity required to start the motor, and if the start inhibit function is enabled, use this information in addition to the thermal capacity used data to ensure that there is enough thermal capacity within the motor for a successful start before a start is attempted. If the relay calculates that there is not enough thermal capacity available within the motor for a successful start, the relay will block the motor start operation until the motor has cooled to a level where its thermal capacity is sufficient for the motor to start. The following is an example to illustrate the start inhibit function. Assume that a motor requires 40% of its thermal capacity to start. If the motor had been running in an overload condition prior to stopping, the thermal capacity would be some value, say 80%. Under such a condition, if the relay had the start inhibit feature enabled, the relay would lock out the motor start until the thermal capacity of the motor had dropped to 60%, such that a successful motor start could be achieved without the thermal capacity used exceeding the volume of the vessel. Now that you understand the concept of motor thermal modeling, we will go into the relay setting. The first step in motor thermal modeling is to obtain accurate motor data from the motor supplier. This data must include the following critical motor information: the motor hot and cold thermal damage curves, the motor rated full load amps, the motor's locked rotor current, the motor's locked rotor stall time when hot and when cold, the motor running and stopped cooling times, the service factor, motor thermal rise, and class of insulation. Note that on many large custom motors, this data may not be supplied as part of the delivery package unless requested by the customer. Further, once the motor has been shipped, it may not be possible to get this data. It is therefore critical that the customer makes it clear to the motor supplier the expectation of complete and accurate motor data being shipped with the motor and its importance as a key component of the delivery. Overload curve selection. The modern digital relay has multiple standard overload curves, which can be chosen to provide accurate protection for the motor. In selecting a curve, the engineer would overlay the standard curves to determine the best fit. The overload curve should be chosen such that it is just below the cold thermal limit and above the hot thermal limit. With the hot-cold curve ratio programmed correctly, the overload curves are automatically adjusted whether the motor is hot or cold. In this motor thermal overload curve, it can be seen that if the running thermal overload curve and the locked rotor overload curve were smoothed into one curve, the motor could not start at 80% line voltage without crossing the curve. A custom curve will allow the user to tailor the relay's thermal damage curve to the motor, such that a successful start can occur without compromising protection, while at the same time utilizing the motor to its full potential during the running condition. The custom overload curve feature allows the users to program their own curves by entering trip times for 30 predetermined current levels. Voltage-dependent overload curve. If you have a very large motor on a weak system, a voltage dip will occur during the start. Under this condition, it is best to use a voltage-dependent overload curve. The overload curve will be dynamic, based on the measured line voltage between the minimum allowable line voltage and the 100% line voltage. This method of protection inherently accounts for the change in motor speed as an impedance relay would. The change in impedance is reflected by motor terminal voltage and line current. For any given speed at any given line voltage, there is only one value of line current. The 469 will shift the acceleration curve linearly and constantly based on a measured line voltage during a motor start. Detail on how to properly construct a voltage-dependent curve will be covered in the 469 settings section of the course. Determining the overload pickup. The protection engineer will typically set the overload pickup to 100% of the motor's capability. For motors with a 1.15 service factor, a maximum pickup of 125% of the full load current can be selected, while the maximum pickup for 1.0 service factor motors is 115% of full load current. Having said this, it is common practice to set the pickup to no more than the rated motor full load current plus no more than 10% of the service factor, unless there is another independent measure of motor temperature, such as stator RTDs. If the motor's winding temperature is also being directly monitored by an RTD biasing function to the thermal model, the overload pickup can be safely increased to the maximum allowable value for that motor. Note that the motor feeder cables are normally sized at 1.25 times the motor's full load current rating, which would limit the motor overload pickup setting to a maximum of 125%. Determining the hot-cold curve ratio. The hot-cold curve ratio can be determined from either the thermal limits curves, if provided, or from the hot and cold safe stall times. If the hot and cold safe stall times are used to determine the hot-cold ratio, simply divide the hot safe stall time by the cold safe stall time. If the thermal limits curves are being used to determine the hot-cold ratio, proceed as follows. From the thermal limits curves, run a line perpendicular to the current axis that intersects the hot and cold curves at the stall point. Draw a line from each point of intersection to the time axis. Record the corresponding times, in this case 10 and 15 seconds respectively. The hot-cold ratio can now be calculated as follows. The hot-cold ratio equals 10 divided by 15, which equals 0.67. If hot and cold times are not provided and only one curve is given, verify with the manufacturer that it is the hot curve which is the worst case. If the supplied curve is the hot curve, then the hot-cold ratio can be set to 1:1. Unbalanced biasing. A balanced three-phase system is one in which the phase vectors are 120 degrees apart and of equal magnitude. If either condition is not met, the system is considered unbalanced. The amount of unbalance is calculated by comparing the positive sequence current to the negative sequence current. A positive sequence set of vectors consists of three equal vectors that are displaced by 120 degrees and have a rotational phase sequence of A, B, C. Negative sequence set of vectors consists of three equal vectors that are displayed by 120 degrees but have a rotational phase sequence of ACB. Negative sequence currents, or unbalanced phase currents, will cause additional rotor heating that will not be accounted for by electromechanical relays and may not be accounted for in some electronic protective relays. When the motor is running, the rotor will rotate in the direction of the positive sequence current at near synchronous speed. Negative sequence current, which has a phase rotation that is opposite to the positive sequence current and hence opposite to the rotor rotation, will generate a rotor voltage that will produce a substantial rotor current. This induced current will have a frequency that is approximately 2 times the line frequency, 100 Hz for a 50 Hz system or 120 Hz for a 60 Hz system. Skin effect in the rotor bars at this frequency will cause a significant increase in rotor resistance and therefore a significant increase in rotor heating. This extra heating is not accounted for in the thermal limit curves supplied by the motor manufacturer, as these curves assume positive sequence currents only that come from a perfectly balanced supply and motor design. The GE multi-lin relay measures the ratio of negative to positive sequence current. The thermal model is biased to reflect the additional heating that is caused by negative sequence current when the motor is running. This biasing is done by creating an equivalent motor heating current rather than simply using average current, I per unit. This equivalent current is calculated using the equation shown. The K factor. The graph on the left shows recommended motor derating as a function of voltage unbalance as recommended by NEMA, the National Electrical Manufacturers Association. Assuming a typical induction motor with an inrush of 6 times FLA and a negative sequence impedance of 0.167, voltage unbalances of 1, 2, 3, 4, and 5% equals current unbalances of 6, 12, 18, 24, and 30% respectively. Based on this assumption, the graph on the right illustrates the amount of motor derating for different values of K entered for the set point unbalanced bias K factor. Note that the curve created when K equals to 8 is almost identical to the NEMA derating curve. If a K value of 0 is entered, the unbalanced biasing is defeated and the overload curve will time out against the measured per unit motor current. K may be calculated conservatively as K equals 230 divided by ILR squared, where ILR is the per unit locked rotor current. For a typical estimate, K equals to 175 divided by I locked motor per unit current squared. For a conservative estimate, K equals 230 divided by I locked motor per unit current squared. Note for synchronous motors, use a K factor of 8. RTD input to thermal memory. GE multi-lin relays also have an RTD bias input to thermal memory function, which also biases the thermal capacity algorithm depending on the stator temperature. When this function is enabled, a second value of thermal capacity used is calculated from the measured stator temperature. This value is used to correct the thermal model, modifying the value of thermal capacity used due to measured, or calculated equivalent, overload currents. The thermal capacity is determined by looking up the corresponding temperature on the programmed RTD bias curve. For example, if the RTD bias curve were programmed as shown, and the maximum stator temperature was 130 degrees Celsius, the corresponding thermal capacity would be approximately 53%. This thermal capacity would then be used if the thermal capacity used from the overload calculation was less. This feedback provides additional protection when errors have been introduced, such as when the cooling has been lost, or incorrect selection of the overload or the ambient temperature is unusually high, etc. It should be noted that the RTD bias feature alone cannot create a trip. If the RTD bias feature forces the thermal capacity used to 100%, the motor current must be above the overload pickup before an overload trip occurs. Presumably, the motor would trip on stator RTD temperature at that time. This completes the motor thermal modeling.
Let's summarize Section 2. This graph represents the 15 standard thermal damage curves that you can select within the motor protection relay settings. The graph is drawn on logarithmic paper where the x-axis represents the multiples of full load amps and the y-axis represents the time to trip in seconds. Curve 1 is the strictest curve, that is to say that it has the least amount of time before a trip will occur in comparison to curve 15, which is the least strictest curve. The curve represents the amount of time that we can afford at different multiples of full load amps before the motor windings become damaged. From a thermal capacity use point of view, once we reach the curve, the thermal capacity used is 100%. Let's take a look at a specific point. On curve 1, if we look at 6 times FLA, we can see that there is only 2.5 seconds available. That means if we have a locked rotor condition, the windings will be damaged in 2.5 seconds. If we look at curve 2, we can see that there is 5 seconds at 6 times FLA. Curve 3, 7.5 seconds. At curve 15, we have 15 times 2.5, which is equal to 37.5 seconds. If the motor is using a soft start, it typically draws around 2 to 3 times FLA, which provides more time before the winding is damaged. This table represents the data to create the curves we saw in the previous slide. The x-axis has the curve number across the top and the multiples of FLA along the y-axis. If we review the trip time values at different multiples of FLA and compare the values between curve 1 and curve 15, you will see the trip times at each multiple of FLA on curve 15 are 15 times larger. This is why it's important to select the right curve. If the curve selected is too sensitive, it could falsely trip on an overload condition. If the curve selected is too lax or too high, then the motor could potentially be damaged before the relay would react. If the standard overload curve is not suitable for your motor application, then you can use the custom overload curve where you modify the curve to meet your needs. For example, if we were to modify the values at 3.0, 3.25, and 3.5 times FLA to 100 seconds, on the graph you can see what the impact is to the shape of the thermal curve. For high inertia motors, the thermal damage curve has a slightly different appearance. 1 represents the running overload thermal limit, 2 represents the acceleration thermal limit at 80% nominal voltage, 3 represents the acceleration thermal limit at 100% nominal voltage, 4 represents the locked rotor thermal limit, 5 represents the motor acceleration curve at 80% nominal voltage, and 6 represents the motor acceleration curve at 100% nominal voltage. The first step is to select a curve that matches the running overload thermal limit of the motor. Next, we enter the values for the allowable line voltage, the line current at minimum V line, the safe stall time at minimum V line, acceleration intersect at minimum V line. Next, we enter the values for the stall time at 100% V line, safe stall time at 100% V line, and accel intersect at 100% V line. These are the thermal damage curves that the relay references depending on the line voltage. The curve on the left represents the thermal damage curve used when the nominal voltage drops to 80%, and the curve on the right represents the thermal damage curve used when the nominal voltage is at 100% of nominal. The relay will shift the acceleration curve linearly and constantly on measured line voltage during a motor start. The thermal overload curves will morph between the two curves depending on the line voltage. Equivalent motor heating current. The relay measures the ratio of negative to positive sequence current. The thermal model is biased to reflect the additional heating that is caused by negative sequence, otherwise known as unbalanced current, when the motor is running. The biasing is done by creating an equivalent motor heating current rather than simply using an average current. If there isn't any unbalance, then the measured current is the I equivalent. The K value is the rating as a function of voltage unbalance that is recommended by NEMA. We'll discuss how this is calculated on the next slide. If you draw a vertical line to the x-axis at the end of the hot and cold thermal damage curve, this is known as the locked rotor amps. It is represented as a percentage of FLA, and K can be calculated in two ways. A conservative calculations, where K is equal to 230 divided by the locked rotor current squared, or the typical calculation where K is equal to 175 divided by the locked rotor current squared. This value is placed into the settings. Motor cooling. The equation thermal capacity used is equal to I equivalent divided by the overload pickup multiplied by 1 minus the hot over cold times 100. This equation is used to determine the steady state value of the thermal capacity used if the motor load remains constant. As a reminder, the overload pickup level is the FLA times service factor. When the I equivalent is higher than the overload pickup level, the motor is heating. If the I equivalent is lower than the overload pickup level, the motor is cooling. In this example, the motor is running at 100% of the overload pickup level and the hot over cold ratio is 0.8. If the load remains constant for 75 minutes, then the thermal capacity used will decay to 20% thermal capacity used. In this example, the motor is running at 80% of the overload pickup level. The thermal capacity used will decay to 16% provided that the load remains the same for 75 minutes. Motor cooling. In almost all of our relays, the cooling time is expressed as a time constant. After one time constant, the thermal capacity used drops by 63%. After two time constants, the thermal capacity used drops by 86%. After three, the thermal capacity used drops by 95%. And after four time constants, the thermal capacity drops by 98%. After five time constants, the thermal capacity drops by 99.3%. Now, if the manufacturer provides a stop cooling time of 150 minutes, then the value that gets entered into the setting is divided by 5. In this example, 30 minutes. If you forget to divide by 5, then the total cooling time is increased by a value of 5. In this example, that equates to 750 minutes. Stop cooling time constant is typically twice as long as the running cooling time based on the cooling from the fan mounted on the front of the motor. Start inhibit. The relays learn three things during each motor start. 1. The amount of thermal capacity used to successfully start the motor. 2. The acceleration time. 3. The average current required to start the motor. We know that when the thermal capacity used value reaches 100%, the relay will trip the motor offline. When the motor has completely cooled, the thermal capacity used value will decay to 0%. If the start inhibit feature is disabled, the start inhibit will block you from restarting the motor until the thermal capacity used value is below 15%. If the start inhibit feature is enabled, it ensures that there is enough thermal capacity within the motor for a successful start before a start is attempted. This is how it is calculated. The relay will review the last 5 starts and take the highest thermal capacity used value and add a 25% buffer to the number. In this example, the highest value was 27% times 101.25 equals 33.75 or 34% thermal capacity used. Now, if the motor trips offline with 100% thermal capacity used, the thermal capacity will start to decay. When the thermal capacity used value reaches 66%, that is 100% minus 34, then the motor start block is removed and the motor can be restarted. Using the start inhibit feature decreases the amount of time you have to wait before the motor can be restarted. RTD biasing. The RTD bias input to thermal model function also biases the thermal capacity algorithm depending on the hottest stated RTD temperature. When this function is enabled, a second value of thermal capacity used is calculated from the hottest measured stated RTD temperature. This value is used to correct the thermal model, modifying the value of thermal capacity used due to measured or calculated equivalent overload currents. The thermal capacity is determined by looking up the corresponding temperature on the programmed RTD bias curve. There is only one thermal capacity used register. Whichever input generates the highest thermal capacity used is the value that is displayed in the register. So let's review our example. In this example, the class of insulation is F. Maximum temperature is 155 degrees C. There are 4 set points to program. RTD bias maximum value, which is set to 155 degrees C. RTD bias minimum value, 40 degrees C, which is considered a cold motor. and RTD bias center value, which is 130 degrees C. The RTD bias center thermal capacity is calculated by 1 minus the hot over cold times 100%. The RTD biasing provides additional protection when errors have been introduced, such as when the cooling has been lost, or incorrect selection of the overload, or the ambient temperature is unusually high. It should be noted that the RTD biasing feature alone cannot create a trip. If the RTD bias feature forces the thermal capacity used to 100%, the motor current must be above the overload pickup level before an overload trip occurs. Presumably, the motor would trip on stated RTD temperature at that time. If an RTD is failing, it could artificially force the thermal capacity used to an abnormal value, blocking the operator from restarting the motor. Verify that all the stated RTDs are within a few degrees of each other. Section 3, Motor Protective Elements. The main focus in this section is to gain an understanding of the fundamental concepts of motor protective elements, such as short circuit, ground fault, phase differential, unbalance, over and under voltage, acceleration timer, mechanical jam, loss of load, starts per hour, time between starts. Let's begin with the introduction to the motor protective elements.
Additional induction motor protective elements. Having a clear understanding of the motor thermal model and how to properly set its components provides us with a good start to the process of protecting an induction motor. There are, however, a few additional protective elements which we will examine. Some of these elements, such as instantaneous overcurrent element, are required to provide adequate protection for an induction motor, while others, such as jam detection, are popular options which may enhance the overall protection scheme. The elements that we will examine are short circuit protection, ground fault protection, differential protection, single phase protection, mechanical jam protection, undercurrent protection, and under and over voltage protection. Short circuit protection. The short circuit element provides protection for excessively high overcurrent faults. Phase-to-phase and phase-to-ground faults are common types of short circuits. The short circuit trip element is coordinated with external upstream fuses such that the element will operate first. When a motor starts, the starting current, which is typically 6 times the full load current rating of the motor, has asymmetrical components. These asymmetrical currents may cause one phase to see as much as 1.7 times the normal RMS starting current. As a result, the pickup of the short circuit element must be set higher than the maximum asymmetrical starting currents seen by the phase CTs to avoid nuisance tripping. The rule of thumb is to set the short circuit protection pickup to a value which is at least 1.7 times the maximum expected symmetrical starting current of the motor. This allows the motor to start without nuisance tripping. It is important to note that the device that the relay is to control under such conditions must have an interrupting capacity equal to or greater than the maximum available fault current. Ground faults. A ground fault is a fault that creates ground faults. A ground fault is a fault that creates a path for current to flow from one of the phases directly to the neutral through the earth, bypassing the load. This current is sometimes referred to as zero-sequence current. Damage to a phase conductor's insulation and internal shorts due to moisture within the motor are common causes of ground faults. A strategy that is typically used to limit the level of the ground fault current is to connect an impedance between the supply's neutral and ground. This impedance can be in the form of a resistor or grounding transformer sized to ensure that the maximum ground fault current is limited to no more than 10 amps to reduce the chances of metal damage to the motor. There are several ways by which a ground fault can be detected. The most desirable method is to use the zero-sequence CT approach. This is considered the best method of ground fault detection methods due to its sensitivity and inherent noise immunity. All phase conductors are passed through the window of the same CT referred to as the zero sequence CT. Under normal circumstances, the three phase currents will sum to zero, resulting in an output of zero from the zero sequence CT secondary. If one of the motor's phases were to short to ground, the sum of the phase currents would no longer equal zero, causing a current to flow in the secondary of the zero sequence. This current would be detected by the relay as a ground fault. The residual ground fault connection. If the cables are too large to fit through the zero sequence CT's window, or the trench is too narrow to fit the zero sequence CT, the residual ground fault configuration can be used. This configuration is inherently less sensitive than that of the zero sequence configuration, owing to the fact that the differential CTs are not perfectly matched. During the motor start, the motor's phase currents typically rise to magnitudes in excess of 6 times the motor's full load current. The slight mismatch of the differential CTs, combined with the relatively large phase current magnitudes, produce a false differential current which will be seen by the relay. This current will be misinterpreted by the relay as a ground fault unless the ground fault element's pickup is set high enough to disregard this error. Phase differential current protection. This feature consists of 3 instantaneous overcurrent elements for phase differential protection. The differential trip element function can only be used if both sides of each stator phase are brought out of the motor for external connection, such that the phase current going into and out of each phase can be measured. The differential element subtracts the current coming out of each phase from the current going into each phase and compares the result or difference with the differential pickup level. If this difference is equal to or greater than the pickup level for a period of time greater than a user-specified delay, a trip will occur. Separate pickup levels and delay times are provided for the motor starting and running conditions. In this example, both sides of each of the motor's stator phases are being passed through a single CT. This is called the flux balanced configuration and is the most desirable owing to its sensitivity and noise immunity. Current unbalance or single phasing protection. The contribution of current unbalance to the thermal capacity used was covered earlier. Here, the magnitude of the current unbalance is used to detect and trip the motor if a single phase condition occurs. Single phase refers to the situation when one of the 3 phases is no longer being supplied to the motor. If enabled, a trip and/or alarm occurs once the unbalance magnitude exceeds the current unbalanced trip pickup for a period of time specified by the current unbalance alarm trip delay. If the unbalance level exceeds 40%, or when the average motor current is greater than 25% of the motor's full load current rating and current in any one phase has no current flow, the motor is considered single phasing and a trip occurs within 2 seconds. Single phasing protection is disabled if the unbalance feature is turned off. Under and over voltage protection. In an under voltage condition, the stator field will be weak. To compensate for the weak stator field, the slip will increase, resulting in increased rotor current and rotor heating. If, on the other hand, the motor is in an overvoltage condition, the increased voltage produces a marginal increase in field strength, but a large increase in stator heating. The rotor will slip a bit less, resulting in a slight decreased rotor current. The overall result of an under or overvoltage condition is an increase in current and motor heating and a reduction in overall motor performance. The undervoltage trip should be set to 90% of nameplate unless otherwise stated on the datasheets. Motors that are connected to the same source may experience a temporary undervoltage when one of the motors starts. To override these temporary sags, a time delay set point has been incorporated into the undervoltage element. The overvoltage element should be set to 110% of the motor's nameplate unless otherwise stated in the datasheets. The undervoltage element can be considered as backup protection for the overload element. If the voltage decreases, the current will increase, causing an overload trip. In some cases, if an undervoltage condition exists, it may be desirable to trip the motor faster than the overload element. Accelerator timer. The relay's thermal model is designed to protect the motor under both starting and overload conditions. The acceleration timer may enhance the motor protection scheme. For example, a given motor should always complete a start within 2 seconds. If the safe stall time is 8 seconds and a failure occurred such that the motor was held in a stall condition, the motor would normally remain at stall for a total of 8 seconds before the thermal model would generate a trip. The accelerator timer could be configured to generate a trip if the motor remained at stall for more than 3 seconds, thereby reducing the stress on both the motor and driven equipment. When enabled, the acceleration timer trip element functions as follows. A motor start is assumed to be occurring when the relay measures the transition from no motor current to some value of motor current. Typically, motor current will rise quickly to a value in excess of the motor's rated full load current. At this point, the acceleration timer will start to time. If the motor's current does not fall below the overload curve pickup level before the program time has expired, the relay will generate an acceleration trip. If the acceleration time is variable, the acceleration timer must be set to a time value slightly longer than the longest acceleration time. Note that some soft starts limit the motor's starting current to less than the motor's rated full load current. Therefore, if the relay does not see the motor's current rise to a value greater than the motor's rated full load current within 1 second after a start, the acceleration timer will be ignored. Mechanical jam detection. If enabled, the mechanical jam element will operate in the following way. After the motor has started, if any one of the motor's phase current magnitudes exceed the jam pickup level setting for a period of time specified by the jam delay setting, the relay will generate a trip. The pickup level for the mechanical jam trip should be set higher than the maximum phase current that is expected under normal operation to avoid nuisance tripping due to momentary load fluctuations. Not only will the mechanical jam detection element trip the motor faster than the thermal overload, but it may also prevent or reduce the damage to the driven equipment. Undercurrent or underpower are 2 ways to detect a loss of load. The undercurrent element. The undercurrent element can be used to detect a loss or decrease of motor current as a result of the loss of load, such as the loss of suction in a pump application or a broken conveyor belt. The second method of load loss detection is to use the underpower element. The underpower element operates as follows. A value other than 0 must be entered to ensure the underpower element is blocked when the motor is stopped. The underpower element is active only when the motor is running and will be blocked upon the initiation of a motor start for a period of time defined by the block element from start set point. This time delay may be useful in applications which require the motor to be running for a period of time before full power is required, as is the case in centrifugal pump or fan applications. When enabled, if the magnitude of the 3-phase total power falls below the pickup level for a period of time specified by the delay, a trip or alarm will be generated depending on how the relay has been configured.
Let's summarize the protective elements section. Short circuit protection. Short circuit protection is for excessively high face-to-face, face-to-ground faults. Short circuit pickup level should be set to 1.7 times the normal RMS starting current to avoid nuisance tripping. Here's an example, short circuit example. If FLA is 347.5 amps, locked rotor amps is 631, the CT ratio is 400 to 5. The short circuit pickup level calculation is as follows. FLA times locked rotor amps times 1.7. In this example, the pickup level works out to be 9.31 times CT. Ground fault. Current flows directly to ground. Damage due to phase conductor insulation. Internal shorts within the motor due to moistures. There's 2 ways to measure ground fault. You can use a core balance zero sequence CT that measures the current. It is extremely accurate. It's unfortunately a little more expensive because of all the amount of iron. Another way is to use the existing phase CTs. This is called the residual CT connection that calculates the neutral current. Current unbalanced single phasing provides a single phase trip if the unbalance exceeds 40% or if the motor current is above 25% FLA and any phase reads no current for 2 seconds. Under voltage over voltage. If there is an under voltage condition, the current drawn by the motor will increase, and as a result the temperature will also increase. If there is an overvoltage condition, the core becomes overmagnetized, which in turn causes an increase in temperature. These settings are typically set to plus and minus 10% of the nominal voltage. Mechanical jam. This element is only enabled when the motor is in a running condition. If any of the phase currents go above normal to a set limit, say 2 times FLA, then a trip command will be issued. This element reacts faster than the thermal overload. Loss of load. There's 2 methods of detecting loss of load. The first one is undercurrent, if there is a loss or a decrease of motor current. And the second one is under power, if there is a loss or a decrease of 3-phase total power. This is used in situations such as loss of pressure in a pumping application, say a belt breaking on a conveyor or a belt. Acceleration. This is time protection to ensure motor successfully starts within a certain period of time. This is time protection to monitor motor transition from a stop to a running condition. Starts per hour. When we select the settings for this element and limitations are detected, starts per hour. When we select the settings for this element, the limitations are dictated only by the thermal capability of the motor. We should follow these rules. If a conservative approach is adopted, set relay based on the starts per hour for a hot motor. If a liberal approach is adopted, set the relay based on starts per hour for a cold motor. And for hot motor situations, this function will be supervised by the thermal model. Element is applied to inhibit the motor start command. If we try to start the motor more times than the setting, a lockout time is initiated until the starts per hour timer resets to 0. Note, an emergency restart clears the lockout time to 0 minutes and resets the pickup and operate operands. Let's take a look at a starts per hour example. Let's program the starts per hour element to 3 and see what happens. During the first start, the first starts per hour counter begins counting down from 60 minutes. If the motor stopped after 10 minutes, the first starts per hour counter would display 50 minutes. If we restart the motor after 10 minutes, the second starts per hour counter would display 60 minutes and the first starts per hour counter would now display 40 minutes. If the motor stopped after 10 minutes, the first starts per hour counter would then display 30 minutes, the second starts per hour would display 50 minutes. If we wait another 10 minutes and start the motor, the third starts per hour counter would now display 60 minutes, the second starts per hour counter would display 40 minutes, and the first starts per hour counter would display 20 minutes. If the motor were to run for another 10 minutes and then be stopped, a start block would occur for 10 minutes until the starts per hour counter reaches 0 minutes. Then the start block would be removed once the counter went to 0. Time between starts. This element is employed to prevent consecutive starting or motor abuse during commissioning or abnormal operation conditions. This element determines the minimum waiting time between 2 consecutive starts. Time between starts example. Let's program the time between starts element to 20 minutes. When we start the motor, the counter begins at 20 minutes and starts counting down. If we stop the motor after 10 minutes, there will be a restart block until the timer resets. Motor status. If no auxiliary contacts from the starter are wired to the relay will assume the motor has stopped if the phase current is less than 5% of the CT primary current, and will detect a start condition when phase current is sensed after a stopped motor condition. If the motor idles at 5% of CT, several starts and stops can be detected, causing nuisance lockouts if starts per hour, time between starts, restart block, or backspin timers are programmed. As well, the learned values such as the learned starting thermal capacity, learned starting current, and learned acceleration time can be inaccurately calculated. This type of problem can occur when a synchronous motor with a fixed field is run at no load. To overcome this problem, a digital input should be configured to read the status of the breaker and determine whether the motor is stopped or simply idling. With the spare input configured as starter status and the breaker auxiliary contacts wired across the spare input terminals, the relay senses a stopped motor condition only when the phase current is below 5% of CT and the breaker is open. If both of these conditions are not met, the relay will continue to operate as if the motor is running and the starting elements remain unchanged. So let's take an example of the motor starting, the motor status. So the stop status is when the relay cannot sense any current. That means the current input is below what the relay can sense. In some relays that's 2% of CT primary, and others that's 5% of CT primary. The next part of the curve is the acceleration, start acceleration status. If the previous status was stopped and the current value is greater than the minimum pickup, this state is maintained until the average current falls below the overload pickup level. Running, as average current is below the overload pickup level and greater than the minimum pickup. An overload status is when the previous state was running and the average current is greater than the overload pickup level. So let's take a look at some of the motor status examples here. In our example, the spare input is configured as a starter status 52A. And if we look at the different examples here, if 52A is closed and the relay is sensing current, then the motor status is running. If the 52A is closed and the relay is not sensing current, then the motor status is still running. If the 52A is open and the relay is not sensing current, then the motor status is stopped. Now, what happens if we have a trip condition and the relay still sees current? This is considered a breaker failure or welded contact. So the next part that we're going to do here is we're going to create a set point file using the motor settings auto configurator. I'll show you the steps in creating a set point file using the motor settings auto configurator. Here's an example of a motor data sheet and thermal overload curve. And we're going to focus on the data needed to be entered into the motor protection relay. So items such as the insulation class, the service factor, the temperature rise, voltage, current, locked rotor amps, acceleration time, number of consecutive starts, cooling time constant. The graph that we also have here, the graph provides the hot and cold safe stall times. Now I'll show you a live demonstration of using the motor settings auto configurator. What I'm going to be using here is the 469 motor settings auto configurator. So here we have the InterVista 469 setup program, and we're going to use the motor settings auto configurator to create a settings file. I'll select the motor settings auto configurator. It will prompt us with a name and location to store it. I'll give it a name such as Pump B. Get a version number. The description is a text block that you can give the file a name, and the serial number lock is basically a means of security that if you put a serial number of a relay in here, then this setting can only be loaded into that particular relay. Now we'll click on next, and it will start prompting us for information. So based on our data sheet, we had a full load amps of 413. We had a locked rotor amps of 550%. The rated voltage was 4,000. Our service factor was 1.0. The safe stall time hot was 7 seconds. Safe stall time cold was 9 seconds. Our installation class was an F, and the motor temperature rise in this case was 85. So we'll switch over to Other and manually type this in as 85. The motor cooling time, now this is motor cooling time constant. The running was 25, and the stopped in our case was 150. There was no information about RTDs. However, I will put them in just the same to show you how it's done. Stator RTDs, we have a choice of 4 different types of RTDs. We can change the multiples of RTDs by 3, and we can set up our bearing RTDs as well. Set up alarm and temperature ranges. Let's put 65 Celsius for an alarm, 80 degrees for a trip. We'll leave the ambient RTDs alone. Let's click on Next. System frequency, we have 50, 60, and variable. Variable is where you use this with a variable frequency drive. So we'll stick with 60 Hertz. Phase rotation, either ABC or ACB rotation. We'll select our switching device, whether it's going to be a breaker or a contactor. If we go with the breaker and select the breaker status as 52A, when I select breaker and select next, what will happen here is this. We'll get a little warning here that indicates that we have to make sure there's enough that the circuit breaker can break the fault current. If I back up, let me just back up here for a moment, and I select the contactor, then it tells us that their short circuit protection will be disabled. So let me go back to the breaker. There we have it. We'll go next. We'll put in our CT primary. So the CT based on our FLA is 413, so I will select a CT primary of 600 amps. I'll put in a ground CT. I have a choice of either residual or core balance. So let's go with a core balance. Sensitive 50 to 0.025 CT. I'll leave the differential alone at this point in time. We'll continue on, click on Next. We'll put in our voltage transformer. I'll put in a Y. We're dealing with a 4000 to 120. So if we're going from 4,000 volts down to 120, which is the inputs into the back of the relay, this is a difference of 33. VTs are normally connected on the line side. Acceleration time at the minimum voltage, for example, was 6 seconds. The acceleration time at rated, 3 seconds. If we go with the conservative number of starts per hour, in our case we'll go with 2 starts per hour. There wasn't any time between starts recorded, but we can put in something as 1. And the motor restart timer, what this represents is if we have a situation where we're pumping water up a hill and we shut the motor off, then the water travels back down to its source and would have a tendency to turn the impeller backwards. And what this timer is basically a timer that allows us to, that basically blocks us from restarting the motor while the water is pushing the impeller backwards. So we'll leave that blank for our application here. And that completes the settings. Now, this thing creates a nice PDF report. Let me just show you this report. So it generates a nice PDF report, gives us the name of the file, the order code, the firmware version, when it was created. It gives us the information that we entered in, the full load amps, the locked rotor amps, nameplate voltage, all the pertinent information that we put in here, insulation classes, motor cooling constants, RTD types, system frequencies, phase rotation. Gives us the warning as certain things aren't enabled. Our current sensing, differential elements that they weren't turned on, the voltage sensing, motor starting information. So as we scroll down further down the page, it now shows us all the configurations that the program did for us. So this is part of the settings. The 413, the 4000, all these different parameters are the settings inside the set point file now. It has selected the overload pickup level for us because we put in a service factor of 1.0, and based on NEMA standards we can push this to 1.15. It calculated the K factor for us. This is using the 230 divided by 5.5 squared, and it comes out with to 7.8, and they rounds it up to a whole number. Our cool time constants, our hot and cold safe stall ratio, this is based on the locked rotor for the safe stall times from the cold and the hot. That was the 7 divided by 9, giving us 0.78. It set up our RTD biasing based on our insulation class and our temperature rise. So here's our 3 different points. And it sets up our alarms and trip levels for our thermal capacity. Short circuit. Once again, this was based on our full load amps times locked rotor amps times 1.7. So in our example here, we were looking at 413 times 5.5 times 1.7, and then dividing it by 600 gives us this value here, 6.4 times CT. We have all our different values here as well for the overload alarm. Mechanical jam, setting it up for 3 times FLA with a 2-second delay. Current unbalance, 15% for 4 seconds for an alarm, 20% for the 1 second for a trip. The ground fault configurations. The acceleration timer based on the information that we put in. The jogging block, the starts per hour, the time between starts. The type of RTD information that we put in for the stator and the bearing. It sets up the alarms for us for the open RTDs and for the shorted RTDs as well. On this page we see the different configurations for the RTDs, for the alarm and the trip levels, for the stators, and then further down for the bearing RTDs. Under voltage settings, over voltage setting, and finally phase reversal. This concludes the protection elements portion of the motor webinar. Once you finish reviewing this, you can now close this file, and it'll bring you back to this main screen. You select finish, and now the settings file has been dropped into the offline window. In closing, I would like to thank you for attending this webinar, and we hope you found it useful and informative. In these sessions, there is not always enough time to answer all the questions or cover all facets of a topic, so try to make a point of attending our future technical webinar offerings as we continue to build our webinar course library. We invite you to stay connected with us through various media such as YouTube, LinkedIn, Twitter, through subscription to our newsletter, our web pages, or simply drop us an email. We do listen to your feedback, and staying connected helps us meet your growing needs. If you register to this technical webinar session, you will receive an email that we've posted the recorded version of the webinar to YouTube. There will be a link to a survey to provide us with feedback. Take advantage of this opportunity to let us know how we were doing. This concludes this session, and I wish you a wonderful day or evening, depending on which time zone you are in. Thank you, and goodbye.